Welcome to today's class. Today we are starting a new chapter, one of the central chapters of this course, namely the one on Fuchsian groups. Very roughly speaking, one can think of Fuchsian groups as being the subgroups of SL2R or PSL2R, with the property that the orbit space of the hyperbolic plane modulo the action of one of these groups has a nice hyperbolic structure or hyperbolic metric, and in such a way that the projection that goes from the hyperbolic plane to this orbit space is a covering map, a covering function, or a ramified covering function, like almost a covering map. Somehow it's precisely the Fuchsian groups, the ones that allow us to obtain these nice structures on the orbit spaces and on the projection from the hyperbolic plane to the orbit space. Where they are going to be defined as simply as the discrete subgroups of SL2R or PSL2R, which means that first we have to develop certain understanding of this concept of discreteness or discretion, and also that we have to understand this notion of discreteness of a subgroup of SL2R or PSL2R in terms of their action, the action of these groups on the hyperbolic plane. So today the Fuchsian groups are not really going to appear today, because today is going to be devoted to speaking about some preliminaries, some topological preliminaries. So let's start with this consideration. So fix a point in the upper half plane, say in U. So pick this point. We're going to keep it fixed for a while. And consider the function that evaluates each matrix at Z0, but not the matrix, but rather its associated Mobius transformation, right? So that to each matrix, what we associate is the image of Z0 on the Mobius transformation of the matrix. So this is the definition. So of course we expect this function to be continuous, and so in the following few minutes, are going to be devoted to a more or less formal argument as to why this function is continuous. So we know that we have a tautological function from the set of non-zero vectors of z squared to P1c, right? I mean that the function that to each non-zero vector associates the one-dimensional subspace spanned by that vector, right? So it's this. I call it the tautological projection. And recall that we used this tautological projection to put a topology here, right? I mean, because it's a surjection. We have a topology here. I mean, we took the analytic topology, and then we said, okay, so put a topology in P1c, put the topology in P1c that has a property that the function is an identification. So, or in other words, a topological quotient, right? I mean that categorically speaking, in the category of topological spaces, this function is a quotient, right? So we did this at the beginning of the course, So I'm just recalling. And so the first, an exercise here would be that if you are given a topological quotient, then kind of if you want the Cartesian product with the identity of any space is again a topological quotient. So recall that, I mean, this function to each pair of points, what it associates is, well, the first entry doesn't change, and the second in the second entry it applies pi. Okay, so if you start with a topological quotient, then by adding an extra factor, you obtain another topological quotient. Okay, and then by this exercise, using this exercise, we deduce that if now we take the product with SL2R, so we take this topological quotient, and then we take the product with SL2R, and then then we obtain a topological quotient, right, by this exercise. So here SL2R is this space Z. Okay, so it's a topological quotient. So this means that we have a commutative diagram of continuous functions given as follows. So first of all, consider this function, which is, you see, this function is the usual function from linear algebra that given a pair consisting of a matrix and a vector, what it does is it multiplies them, right? So it evaluates the matrix in the vector, right? So that's this function. That one is continuous, no problem. But the point is that it induces a function from this product to P1C, right? I mean, because this, we saw that given a matrix, since it sends one-dimensional subspaces to one-dimensional subspaces, well, we can instead take the matrix and now a one-dimensional subspace, and then what do we do now? Well, we do this, right? And then it's an induced function, right? So here this one is an induced function. It's induced from this one, right? And so since we know that this one is a topological quotient, which is precisely the exercise. So since we know that this one is a topological quotient, we know then that this one is continuous. So that's why I wanted to have this exercise. Okay, so now we know that this one is continuous, but then if I use the homeomorphism to pass to C bar, right? And of course here I preserve the first factor, but in the second factor I switch to C bar, and in P1 I switch to C bar, so that these are actually homeomorphisms. Then what I obtain is that the function at this level, at the level of C bar, that corresponds to this one, is also continuous. But that one is of course given A and a point in C bar. A point in C bar is what corresponds to a one-dimensional subspace of C squared. It associates this point, which is precisely the point that corresponds to this one-dimensional space in P1C, right? So since this one is continuous, I obtain that the orange one is continuous. Okay, and then you see, and then what I do is, well, I start specializing. right? Because I know that here inside C bar I have U, inside C bar I have U, and the inclusion is of course continuous. The inclusions are continuous. Okay, and here this function restricts to a function here because I know that the matrices in SL2R preserve U bijectively, right? And by this I mean the corresponding Mobius transformations. Okay, but I go one specialization, one further specialization, because here in U I simply restrict to Z0. So I have this space, which is pretty much SL2R, but kind of decorated with Z0, right? Okay, and then I include SL2R in the first coordinate, right, of this decoration. And then, but then you see, since this one was continuous, this restriction is continuous, hence this restriction is continuous, hence the function I wanted is continuous because this one here, what does it do? It precisely takes a pair A, Z0 to mu A of Z0, which was precisely the correspondence rule of that evaluation at Z0. So indeed, my function is continuous, and I was kind of course, this I could have taken for granted from to begin with, and maybe I was a bit pedantic. I just wanted to have kind of every step compartmentalized and to see that the key fact is this exercise, that when you add an extra factor to a topological quotient, you obtain another topological quotient. Okay. Now, a theorem which is going to be very useful. So again, they give me a point in U, and now they give me a compact subset of U. And what I claim is that the inverse image of K, which consists, of course, of all the matrices in SL2R with the property that mu A of Z0 lands in K, that inverse image is compact. I mean, it's a compact subset of SL2R. Okay, so first of all, it is closed. Well, yes, because the evaluation is continuous. That's what we just proved in the previous lemma. Right? So since K is compact in U, and U is open in R2, right? So K is closed and bounded in R2. In particular, it's closed. So since the function is continuous, this one is closed. Okay, now we are going to show that this one is bounded as well, and then conclude that it is compact, knowing that it's closed and bounded. Now, what I'm going to do is I'm going to show that the four possible entries of any element of this inverse image are bounded. Okay, so now since K is compact, there are positive constants that are witnesses of the compactness. But so one is that the norm of all elements of K is bounded by above by M1. So in particular, for all elements in the inverse image, when I land in K, the norm is bounded. This is just because k is bounded. But also you see the imaginary parts of the elements of U, they are all positive, but the infimum of all possible imaginary parts of elements of U is 0. Right? But K be compact, the imaginary parts cannot tend to 0, right? So they have to stop somewhere above 0. So that's what this says, that all the imaginary parts of elements of K, and hence also for mu A of Z0 are greater than this other positive constant. So that also follows from compactness. And now I'm going to start manipulating these two inequalities. So let's write Z0, which remember that Z0 is somehow fixed once and for all, right? We're not going to move it, at least not during this proof. So write it as x0 plus y0 I, where of course these x and y I assume them to be real numbers. And let's take any element in the inverse image of K. Okay, any, right? So the only assumption is this one. No extra assumption is going to be made whatsoever. So this inequality becomes this inequality, of course. The first inequality becomes this inequality, and that's obvious. Right? Now, the second inequality. Here, we know that this imaginary part is positive, so it's equal to its absolute value, right? On the one hand. On the other hand, we had at some point computed this imaginary part, and we saw that it was equal to the imaginary part of Z0 divided by this square. Right? So putting absolute value, what I obtain here norm square. So the second inequality becomes this inequality. Okay. And now from the second one, what I deduce is the following. So first, pass this one to the left and this one to the right. And we obtain this inequality. And now compute this norm. Right? So alpha, beta, gamma, and delta are real because A has been taken in S2R, which means that somehow, like the only here delta is real, so the only possible imaginary part can come from Z0. So we obtain this square and this other square. I mean, this is the norm square. Okay, but then of course to this number I'm adding something non-negative, so this is greater or equal than just one of the two summas. Okay, now this means that when I take a positive square root, here I have absolute value, but y naught is positive, so I can just pass y naught dividing, and I obtain this inequality. Okay, now looking at that inequality, I notice that this number is absolutely independent of gamma. Right? So this means that what I find is that gamma is bounded. Gamma is bounded. Okay, so we have been able to bound one entry of my arbitrary matrix. I mean, arbitrary in this inverse image, right? Which is in particular contained in SL2R by definition of the function Z0. Now, let's go on to alpha. So using this one, I pass this one to the right, and I obtain this, and this. Well, I know that this number is you see here I use this inequality. right? So I know that this number is less or equal than m1 times the square root of this thing. Okay, and then you see that then I can apply the same argument I used for gamma here, right? I mean here, I mean I kind of forget about this part, this intermediate part, and then if you will take square, and then you see you are just you just remain with alpha y naught, and then kind of it's the same. It's a similar argument as how we bounded gamma to see that alpha is also bounded. Okay, why? I mean, because what we find is a constant. Well, it's a little modification of this one, right? It's one has to divide by y naught, but that doesn't depend on any of the entries alpha, beta, gamma, delta at all. So alpha is bounded, and and that now for beta and delta, now the story is very similar, because now we take so you see we have where is it? So I think it's here. Let's use this one. And this one, let's multiply on both sides by the square of the norm of z naught inverse. Right? So so here that part becomes this one, and the part on the right, well, here is the factor I multiplied. The point is, I arrive. I mean, here this is a constant independent of alpha, beta, gamma, delta, and on the left-hand side, I arrive at a shape, similar to the shape that here allowed me to bound gamma. Right? I mean, here it was the fact that gamma was accompanied by this z naught. So now delta is accompanied by this z naught inverse. And then, in other words, now you write z naught inverse also as a real plus I times imaginary part. And then you see that delta is also bounded. And for beta, then you use the same trick, right? You know that this is less than this, and then again multiply by z naught by the absolute value of z naught inverse, by the norm of z naught inverse. And then again, what you are doing is here you have a constant, and you are putting this one in a shape that allows you to bound beta in a similar way as how here this shape allowed you to bound alpha, or here this shape allowed you to bound gamma. Okay, so we went entry by entry, showing that they are all bounded. So this set is closed and bounded, where? Well, in SL2R, by definition of the function, of course. But SL2R, I mean, is the preimage of 1 on the determinant function, right? So it's closed in R4. So this one is a closed bounded subset of a closed subset of R something, R to the n. Right? So it's compact. Okay, so it's compact. So let's do some computations, and then maybe try to make have certain intuitive idea how such inverse images look like. So take well, of course, the kind of the most obvious compact sets that come to mind are just the compacts that have only one point. Right? Okay, and among those that have only one point, what's the most obvious one? Well, the one that is exactly z naught. Right? Okay, but you see this one is and here, yeah, this one is the matrices. The matrices whose Mobius transformations, whose associated Mobius transformation fixes z naught, right? So it's kind of the stabilizer of z naught in SL2R according to the action of SL2R in U given by Mobius transformations. Well, if you think about this, this one is S1, right? Then kind of the matrices that fix, whose associated Mobius transformation fixes Z0 is S1. Yeah, sorry. Here I'm mixing some ideas. Let's say P, and then maybe here, let's say something like that. You know, the induced one, kind of. I mean, if I just leave it like this, is not correct, right? But or I don't know, a bar, let's say, inverse. Yeah, so that I really know that it's a circle. Okay. Now, again with this bar, if you will, here I'm defining F Z0 from PSL to R to U. And you see the kind of a Mobius transformation goes to its evaluation at Z0. Okay. Okay. So we know how certain inverse image looks like, which is just a circle, compact. And you see, and given any other element, well, of course, I can pass from this one to this one, right? I mean, all I need is take an element of PSL2R that takes Z0 to W0. Just take one of them, and then you can go from this one to this one, composing, right? So composing anything here, pre-composing by the one, by the specific one, sending Z0 to W0 I took. Right? Of course, which one I take is up to me, right? So while I exhibited you how to show that these one are homeomorphic, there is a non-canonical choice, right? So they are homeomorphic, but I would say non-canonical. But in any case, this one, at least I know it's homeomorphic to a circle, right? So somehow it seems that given, let's say that I take certain, let's say, region in U. Let's say that I take a certain region in U. This is too nice. I don't want that nice. Okay. In U, right? Okay. So it seems that that these inverse images, I mean, these inverse images are homeomorphic to the circle, all of them, right? So in PS, so it looks like in PSL2R, how to say, if I write it vertically, maybe it's more. I mean, from PSL2R, the fiber looks like. Let me copy paste. It looks like I have here, but so you see the function is kind of at each point the inverse image is a circle. So Of course, one thing I don't know yet is whether this inverse image, this would be the inverse image, F Z not inverse of my set, if this was, let's say, K. Of course, one of the things I don't know yet at this point, I don't know if it's true, is whether this is homeomorphic to K cross S1, right? I mean, at this point, I only know by this example that that for each point the preimage is homeomorphic to a circle, but like this circle and this circle, the homeomorphism I constructed was not canonical. It depended in a choice. But of course, let's say that here is Z naught, and that this is kind of the preimage of Z naught, kind of that this is the special one, right? Because Z naught was fixed once and for all. Of course, there's a question, and maybe here I forget a little bit about K, and I rather think that this is rather like let's say an open set, or that some set having Z naught in its interior. Right? Something that maybe happens, maybe not. That maybe there's some neighborhood here. In such a way that you see, I mean, at least from the inverse image of Z naught to itself, there is one homeomorphism that pops up, which is the identity, right? The identity of that circle. And so somehow, yeah, okay. And then to pass to another point, to give the homeomorphism between the inverse image of Z naught and the inverse image of the other point. What I used was an element of PSL2R sending Z naught to my new point. Right? So, but maybe one can pick that element of PSL2R kind of in such a way that you see that when I start considering points closer and closer to Z naught, the corresponding element of PSL2R approaches the identity, which is the one I want here. I mean, which is the one that would tell me which would give me that I pick the identity as a homeomorphism from the inverse image of Z naught to itself. And maybe if I do that, then maybe what I would obtain is that here in this open set, the preimage of this open set would be homeomorphic, or let's say equivalent to this open set cross S1, right? Because somehow I would be able to move all the circles kind of to in kind of, let's say, in a consistent way to the circle at Z naught. Of course, everything I've said right now is only intuitive, but it would go into the direction of this exercise. You see, is this a fiber bundle? And then maybe let me write for this other one that goes from PSL to R. Is it a fiber bundle? I mean, if what I said here about this open set, blah, 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 can't be done, then it would look like maybe the answer is yes. Okay, and if so, is the whole thing the trivial bundle? In other words, this trick that I said about kind of picking for each point, picking an element of PSL2R that goes to there in such a way that everything you know, when you that somehow you can move throughout U in a consistent way, whatever this means. If this can be done all throughout U, then it would seem that the answer would be yes as well here. Right? Okay, so this I leave you as an exercise. Of course, one would have to be like way more formal than I have been now. Right? But I think it's an interesting exercise. By the way, notice that here this theorem. Once we have this theorem for SL2R, then it is also true for PSL2R, right? Because the relation is that f z naught inverse of k, when I project to I mean, this is in PSL2R, right? When I project to the quotient group PSL2R, I don't know how to, I mean, let's say P of projection to SL2R. This is precisely Z naught bar inverse. Okay. So if this we knew was compact, this is also compact. Right? So okay. All right. So that was kind of one first topological aspect, which is which is to locate certain compact subsets of SL2R and certain compact subsets of PSL2R. Okay. Why? Because compact subsets allow us to decide whether something is discrete or not. That's the point. Yeah? So, but the thing is, what is a discrete subset of a topological space? Well, a subset S of a topological space is discrete if when I give it the induced topology, the subspace topology, that topology is the discrete topology, which kind of in relation to X, it amounts to for every S, for every element, there existing an open subset of the big space, which is witness that every single point is open in S with the subspace topology. Right? So I said it more complicated than it really is. So if around every point of my subset there is an open subset of X, so with the property that the given point is the only element of S lying on that open set. Okay, so that is to say that a subset is discrete. Examples, well-known example, right? The integers are discrete in R. This one is discrete in R, like 1 over n, the set of all multiplicative inverses of positive integers. These are discrete subsets of R, even though it has an accumulation point in R. Right? I mean, it does have an accumulation point, but it itself is still discrete, right? Because the points that do belong to it are really separated one from the other. That's the thing, right? And the point where they accumulate is not even the set. So, okay. Now, if I glue that point, well, this is no longer going to be discrete, right? Because any open set around this guy contains other elements. Okay, so you see, so we see that somehow what it looks like is that a subset S of a topological space X is discrete if its points, if the points in S are not accumulation points of points in F, right? So somehow a subset is discrete when it doesn't accumulate inside itself, right? That maybe it accumulates, but whenever, if there is any accumulation point, that accumulation point is a fortiori outside S. That's discrete. This looks a little bit, this sounds a little bit strange, but when one has the extra condition of the set being closed, that is of the set S containing all of its possible accumulation points in X, the notion really simplifies. I mean, it's easier to think about this notion. Right? So actually, if you have a closed set, that is a set that contains all its possible accumulation points, well, it's discrete if and only if it doesn't accumulate in X, right? Because, well, yeah, right. I mean, being closed, it's containing all possible accumulation points that may lie in X. They are already there. Right? And being discrete is not accumulating in yourself. Right? So if you are closed, then you don't accumulate in X whatsoever, because you don't accumulate in itself, and also not outside, because then you wouldn't be closed. Okay, and I know closed sets are not persons, right? But okay. Okay, so that's that. For closed sets, it is way easier to think about discreteness. And actually, not accumulating in X at all is equivalent to being closed and discrete. Okay, which I would say this is kind of this is the intuition one usually has in mind. Anyway, and this is just a series of exercises to play with those notions. Okay, now as I said, we are going to introduce the Fuchsian groups as the discrete subgroups of SL2R or PSL2R. Okay, and then you see that I mean, pretty much we see that if a subset is not closed, then it being discrete doesn't prevent it from accumulating in the total space. So it may sound like discreteness is not a good notion, right? Or like in order to really have a good notion, you really have to consider or well-behaved notion of discreteness. You really need to impose closed and discrete. Okay, so this lemma says, okay, if you take a subgroup, then you don't have to worry about discrete subsets that maybe have accumulation points in the total space. That is, if you have a Lie group G, SL2R is a Lie group, PSL2R is a Lie group, and if you have a subgroup, that one, then the following two conditions are equivalent. The subgroup is discrete, and the subgroup does not accumulate not only in itself, but in the whole space. I.e., no? Okay. Before proving the lemma, like an obvious corollary, every discrete subgroup of a Lie group is closed. An exercise, maybe a challenging exercise, would be to which extent can we put here some more general, more general groups not only Lie groups, but can we put arbitrary topological groups here? And the corollary is still the corollary is still true. If not, what are there any kind of weaker conditions than the group being a manifold that one can replace this with? I would say that's like a quite challenging exercise. Anyway, let's prove the lemma. So this one is obvious because being discrete is not accumulating in itself. Right? Sorry, this one is obvious because being discrete is not accumulating in itself. So if you already know that it doesn't accumulate anywhere in G, then it doesn't accumulate in itself. So the hard part is this one. Okay, so suppose it's going to be a contrapositive. Suppose that it does accumulate at some point. And so it does accumulate at some point. Formally speaking, this really means that every open set containing this element necessarily contains at least one element of gamma different from this G. The part about being different is no problem because gamma is discrete, but you see the fact that we're working with a Lie group allows us to deduce that then there actually is a sequence of elements of gamma that tends to G. So in other words, that being in a Lie group allows to deduce that accumulating at one point implies that we can pick a sequence that converges to that point. And of course, there still is the question of what, formally speaking, what does it mean to tend to converge to that point in a Lie group? I would say it's not so hard to say, but this exercise 82 is not so hard to say because G is a Lie group. I mean, it's a manifold. So let's say an informal way of seeing it, of considering of thinking is that, you know, G is a manifold. So if you can even speak about differentiable functions, how are you not going to be able to speak about what it means to converge, for a sequence of points to converge? Right? Of course, you have to be able to. Right? I mean, this is kind of a bit, this is like super informal way of seeing it, right? But a more formal way of seeing it, I would say, is okay, pick a chart, and then once you pick a chart, with that chart, you have some open homeomorphic to R to the n, and to an open set in R to the n, and in this open set of R to the n, you have the notion of converging. Right? So that a sequence converges. Maybe I would say, okay, is at first that given any chart, you know, that given any chart around the point of alleged convergence, the sequence at some point just contains elements only in that chart, and once you are there, then you satisfy the notion of convergence with map, you know, by just simply kind of copying and pasting the notion of convergence in Rn. Right? But anyway, the formal exercise, I leave it to you. So there are two things already there, right? That first, that the fact that we are working in a Lie group tells us that the notion of the topological notion of accumulation translates into the existence of a sequence that converges. That's kind of the first exercise on topology. And the second one is, what does it really mean formally? Okay, this I leave to you. And you see, the thing is actually, since it's accumulation, one can actually say, okay, I mean, the sequence that you pick it kind of, you can pick it in a sequence that you pick. You pick it actually kind of it is possible to pick it with a rather specific property that it does not repeat elements. I mean, this you can do. I mean, it is possible because it's a sequence that comes from accumulation. Okay. Now, once we have this sequence with no repetition, so pairwise distinct elements, converging to our point, okay, then somehow now we manipulate it to force it to converge to an element of gamma, right? Now, elements of gamma, kind of the only obvious element in gamma we have, or we can have a graph on, is the identity. Right? So how do we obtain the identity? Well, as something times its inverse, but we want to obtain it as a accumulation. So we multiply, each element by the inverse of the next one, right? Because the limit of the sequence obtained that way is going to be the identity, which lies in gamma. So this one is a sequence of elements of gamma, none of which is the identity because there were no repetitions in the original sequence. So we have a sequence of elements of gamma, none of which is the identity, and converges to the identity. Okay, but then this means all of this means that that there exists a subsequence consisting of only pairwise distinct elements of this sequence, right? Because that sequence is not stationary. Okay, and then with that subsequence, we see that the identity is an accumulation point of gamma. So we see that if gamma accumulates in G, then gamma accumulates in itself, namely in the identity. So we prove that not this implies not this, so we are done. Okay, this exercise, right? And then one more exercise a couple of claims that we use are indeed true, namely that if you have this link that this sequence tends to this in a Lie group, then the sequence of inverses tends to the inverse, first of all, and second, that if you have two sequences that converge to elements in the Lie group, then the sequence of products converges to the product of the limits, which we use, right? I mean, we used both of these facts we used here, right? I mean, here we are using both. Okay, and finally, an exercise, you see, a property that we are going to use, I think, quite frequently, which is, okay, you are given your Hausdorff space. I mean, a Lie group is a Hausdorff space, right? Or think about SL2R, it is, of course, a Hausdorff space. Okay, and say that we have a closed and discrete subset of X. Then show that for any compact, the intersection is finite. It's easy, it's an easy exercise. And of course, is the converse true, right? I mean, given your Hausdorff space X, if the intersection with any compact is finite, does that mean that your subset is necessarily closed and discrete? Okay, and then I think we are done with topological preliminaries. Okay, so we're going to start. I think tomorrow we are going to define what is a Fuchsian group and to characterize Fuchsian groups. You know, to give a characterization that tells me when a group is Fuchsian in terms of its action on U. Right. So what does it mean geometrically to be Fuchsian? Okay.